For thousands of years, humanity's progress has been measured not only by the monuments we built or the wars we fought, but by something quieter, the way we calculated. From the clacking beads of the abacus to machines that now manipulate quantum states, each step in our computational journey has reshaped society. What began as a tool for merchants to track grain and trade routes has grown into systems that guide spacecraft, simulate the climate, and decode the building blocks of life. Each leap in calculation has carried with it new revolutions in science, in commerce, in communication, and today, as quantum computers begin to challenge the very limits of classical logic, we are reminded that the story of computation is far from complete. This is the tale of how simple counting devices evolved into engines of unimaginable power, and how, at each stage, humanity calculated not just numbers, but its own future. Before silicon chips, before electricity, even before written numbers, there was counting. Humanity's first steps toward computation were born of necessity, tracking food stores, measuring seasons, and recording debts. The earliest evidence lies in tally sticks, notched bones used in Europe and Africa more than 40,000 years ago. Each mark represented a count, a primitive yet profound recognition that numbers could be externalized, stored outside the human mind. As civilizations grew, so did their need for order. In Mesopotamia, clay tablets inscribed with cuneiform served as ledgers, recording trade, taxation, and astronomy. The Egyptians used hieroglyphs to note harvests and pyramid construction. In ancient China, bamboo strips tracked goods along vast trade networks. Numbers were no longer just abstractions. They became tools of empire. Then came the abacus, a device so simple yet enduring that versions of it remain in use today. By sliding beads across rods or grooves, merchants and officials could add, subtract, and multiply far faster than mental arithmetic alone. In China, the swanpan became a symbol of commerce. In Rome, the calculi gave us the very word calculate. These tools democratized computation, moving it from the scholar's scroll to the trader's stall. Parallel to these devices was the development of written numerals. The Hindu-Arabic numeral system, with its revolutionary concept of zero, spread through the Islamic Golden Age into medieval Europe. This leap simplified arithmetic, enabling calculations that Roman numerals made cumbersome. Without it, modern mathematics, and by extension modern computing, would have been impossible. The Greeks, meanwhile, pursued the philosophy of numbers. Thinkers like Pythagoras and Euclid explored geometry and proportion, framing mathematics as both a practical science and a key to understanding the cosmos. Archimedes designed ingenious mechanical devices, war engines, water pumps, even an odometer, showing how numerical thought could transform the physical world. Yet for centuries, calculation remained largely manual. Devices like the astrolabe allowed navigators to chart stars and sailors to cross oceans, but they did not automate thinking. The dream of a machine that could reason with numbers lingered at the edge of imagination. It would take the Renaissance and the rise of mechanical ingenuity to push that vision forward. The seeds, however, had been planted. From tally marks to Abacus, from zero to geometry, early human innovations laid the intellectual and practical foundation for computation. Each culture added a brick to a structure they could not yet see, a structure that would, over millennia, grow into the towering edifice of modern computing. The leap from counting devices to true computational machines came in the early modern period, when mechanical ingenuity merged with mathematical ambition. By the 17th century, Europe was experiencing an explosion of trade, science, and navigation, each demanding faster and more reliable calculations than quills and Abacus could provide. Out of this need emerged the first prototypes of automated computing. In 1623, Wilhelm Schickard, a German polymath, built what is often called the first mechanical calculator. His calculating clock used gears and wheels to perform addition and subtraction. Though only one was built and later destroyed in a fire, it hinted at a future where machines could handle repetitive arithmetic with precision. Soon after, Blaise Pascal introduced the Pascaline in 1642, a brass machine of interlocking gears, capable of adding and subtracting large numbers. Motivated by his father's taxing job as a French tax collector, Pascal sought to ease the burden of endless arithmetic. Though expensive and limited in function, the Pascaline was a marvel, a tangible proof that math could be mechanized. Gottfried Wilhelm Leibniz pushed the concept further with his stepped reckoner in 1673, which could multiply and divide as well as add and subtract. Leibniz also articulated the dream of binary arithmetic, reducing all numbers to combinations of ones and zeros. This idea, though underappreciated at the time, would centuries later become the cornerstone of digital computing. While these calculators addressed arithmetic, others dreamed of programmable machines. In the 19th century, Charles Babbage, an English mathematician, envisioned the difference engine to automate the production of error-free mathematical tables. Though plagued by funding issues and never completed in his lifetime, it inspired his grander design, the analytical engine. This proposed device featured a store, memory, a mill, processor, and input-output mechanisms, the essential architecture of modern computers. Working alongside Babbage, Ada Lovelace recognized something profound. She understood that the analytical engine was not just a number cruncher, but a universal machine capable of manipulating symbols according to rules. Her notes included the first published algorithm intended for a machine, earning her the title of the world's first programmer. In parallel, mechanical aids proliferated. The Jacquard loom, invented in 1804, used punch cards to control weaving patterns. This method of encoding instructions into a machine foreshadowed computer programming. Similarly, Herman Hollerith applied punch cards in the late 19th century to tabulate the 1890 U.S. Census. His company eventually evolved into IBM, a name inseparable from the history of computing. Public reaction to these breakthroughs was mixed. To some, mechanical calculators were fascinating novelties. To others, they threatened traditional crafts or seemed impractically complex. But among scientists, engineers, and governments, the promise was clear. Machines could extend the reach of human intellect. By the dawn of the 20th century, humanity had moved from tally sticks to machines capable of complex, automated calculations. These breakthroughs did not yet give rise to computers as we know them, but they lit the spark, proving that thought itself, once considered uniquely human, could be imitated by gears, levers, and logic. The story of computation did not accelerate smoothly. It advanced in bursts, driven by war, commerce, and scientific ambition. From the dawn of the 20th century to the digital age, each decade introduced milestones that pushed calculation closer to the boundless systems we know today. At the start of the 1900s, mechanical calculators became common tools for accountants, engineers, and governments. Firms like Burroughs and Monroe manufactured desktop machines that could rapidly add and multiply. These devices, powered by hand cranks or electricity, were less visionary than Babbage's dream, but far more practical. Hollerith's punch card system spread worldwide, allowing banks, insurance companies, and census bureaus to handle enormous data sets. Data processing was no longer theory, it was infrastructure. By the 1930s, humanity stood at the edge of the electronic revolution. Konrad Zuse, a German engineer, built the Z3 in 1941, widely considered the first programmable digital computer. Using relays and binary arithmetic, it executed stored instructions, a step closer to Babbage's vision. In Britain, Alan Turing published his landmark paper on computable numbers in 1936, describing the conceptual Turing machine. Though purely theoretical, his model defined the limits of mechanical reasoning and became the foundation of computer science. war became the greatest accelerator. The Allies needed machines capable of breaking codes and performing ballistic calculations at unprecedented speed. In Britain, the Colossus was built in 1944 to crack German ciphers, using vacuum tubes for lightning-fast operations. Across the Atlantic, the US Army funded the ENIAC, an electronic giant capable of thousands of calculations per second. ENIAC's success in 1945 proved that electronic computation could outpace anything mechanical, changing the trajectory of science and warfare. The post-war era witnessed the spread of electronic computers beyond military labs. IBM introduced the IBM 701, its first commercial computer in 1952, followed by the immensely successful IBM 650. Universities and corporations began to see computers as tools for research, finance, and industry. The invention of the transistor in 1947 by Bell Labs and its refinement in the 1950s replaced bulky vacuum tubes with compact, reliable alternatives. This shift laid the groundwork for miniaturization. The 1960s marked the era of mainframes, massive, centralized machines that powered banks, airlines, and government agencies. IBM's System 360, launched in 1964, was revolutionary, a family of compatible computers that allowed businesses to scale without rewriting software. At the same time, the seeds of the Internet were planted. ARPANET, the U.S. Defense Department's experimental network, demonstrated that computers could communicate, turning machines into nodes of global information. The 1970s delivered the breakthrough that would transform society, the microprocessor. In 1971, Intel released the 4004, a chip that packed an entire CPU onto a single silicon wafer. Suddenly, the power of a room-sized computer could fit in the palm of a hand. This enabled the rise of personal computing. Hobbyist machines like the Altair 8800 inspired young innovators, among them Bill Gates and Steve Jobs, to see a future where every home might own a computer. The 1980s brought the marriage of hardware and software. The IBM PC, launched in 1981, standardized personal computing, while Microsoft's MS-DOS and later Windows created accessible user interfaces. Apple's Macintosh introduced the graphical user interface, making computers friendlier to the masses. Meanwhile, Moore's law, the observation that transistor counts doubled roughly every 2 years, seemed unstoppable, driving exponential growth in power and shrinking costs. Computation leapt from the desktop to the network. The invention of the World Wide Web by Tim Berners-Lee in 1989 and its public adoption in the 1990s transformed computers into portals of global connection. Information, once confined to libraries and offices, became instantly accessible. E-commerce, email, and search engines redefined daily life. Supercomputers also advanced, enabling simulations of weather, nuclear reactions, and the human genome. The new millennium shifted computation once more. Smartphones, powered by ever smaller chips, placed pocket-sized computers in billions of hands. Apple's iPhone, 2007, and Android platforms turned computation into a mobile, ubiquitous companion. At the same time, cloud computing allowed data and applications to live on remote servers, accessible anywhere. The concept of owning a single machine gave way to an ecosystem of devices connected through vast digital networks. The explosion of data from social media, sensors, and commerce demanded new computational paradigms. Graphics processing units, GPUs, originally built for gaming, proved ideal for machine learning. AI systems began outperforming humans in tasks from image recognition to strategy games. Companies like Google, Amazon, and Alibaba leveraged cloud infrastructure to harness data at planetary scale. The computer had evolved from a calculating engine into an intelligent partner. Today, the frontier is quantum computing, machines that manipulate qubits rather than bits. Exploiting superposition and entanglement to solve problems classical computers cannot. Companies like IBM, Google, and startups worldwide race to achieve quantum advantage, where quantum machines outperform traditional ones in meaningful tasks. Though still experimental, the promise includes breakthroughs in cryptography, material science, and drug discovery. Across these decades, rival technologies rose and fell. Vacuum tubes gave way to transistors, magnetic tape to solid-state drives, and proprietary mainframes to open-source software. But the momentum never ceased. Each milestone carried us from physical beads to abstract algorithms, from isolated machines to global networks, from predictable logic to quantum uncertainty. The ascent of computation is not merely technological, it is civilizational. With every advance, humanity has recalibrated how it works, learns, fights, and dreams. From tally sticks to quantum chips, each step was not just a new way to calculate, but a new way to think. The transformation from niche innovation to daily necessity is where computation truly reshaped civilization. For millennia, calculation had been the domain of merchants, astronomers, and bureaucrats, tools of trade, governance, and science. But in the latter half of the 20th century, computation crossed a threshold. It stopped being a specialized craft and became a universal utility, woven into the fabric of modern life. This revolution was not about transistors or algorithms alone. It was about how societies, economies, and human behavior evolved around them. The arrival of the personal computer in the late 1970s and early 1980s marked a cultural turning point. Devices like the Apple II, Commodore 64, and IBM PC were more than machines. They were invitations to a new way of interacting with information. For the first time, ordinary people could write programs, manage household budgets, or play digital games without stepping into a laboratory. Families gathered around screens, much as they once did around radios or televisions. The idea that computers are for scientists dissolved, replaced by a sense that they were for everyone. Education quickly followed. Schools introduced computer literacy courses, and students learned programming alongside reading and mathematics. Universities embraced computational modeling, revolutionizing disciplines from physics to linguistics. This democratization of computing knowledge meant that innovation was no longer confined to elite institutions. A teenager in a garage could create software that would change the world. As computing became mainstream, it redefined economies. Entire industries, software, semiconductors, IT services emerged from nothing, creating millions of jobs and trillions in market value. Businesses transformed how they operated. Spreadsheets replaced ledgers, email replaced memos, and databases became more valuable than filing cabinets. By the 1990s, the rise of the internet supercharged this transformation. Companies like Amazon, eBay, and Google showed that commerce, search, and advertising could exist entirely online. The digital economy, once a niche experiment, became the backbone of global trade. Nations that invested in computing infrastructure found themselves leading new markets, while those that lagged risked being left behind. The spread of computation also rewrote the rhythms of daily life. The internet connected distant communities, social media collapsed geographic barriers, and messaging apps turned communication into an instant global activity. Families separated by oceans could talk face-to-face in real time. Ideas spread virally, shaping politics, culture, and collective behavior in ways unthinkable in the pre-digital age. This new connectivity also changed identity itself. Online personas, once an oddity, became extensions of self. People curated digital lives, built communities around shared interests, and found platforms for activism, creativity, and expression. Yet this revolution brought challenges: misinformation, privacy erosion, and new forms of surveillance. Society was forced to grapple with questions about trust, truth, and autonomy in a computational world. Computation also transformed the nature of work. Automation replaced repetitive tasks, from factory assembly lines to data entry desks. At the same time, it created new professions, software engineering, cybersecurity, data science, that did not exist a generation earlier. The workplace became digital, distributed, and global. Telecommuting, once a novelty, became mainstream, culminating in the remote work revolution of the 2020s. But these shifts were not without tension. Workers faced displacement, governments debated regulation, and societies wrestled with inequality born from technological disruption. The computational revolution brought immense prosperity, but it also demanded new skills, policies, and ways of thinking to manage its impact. Perhaps the deepest change was cognitive. Computation altered how humans approached problems. Algorithms taught us to think systematically, to see patterns in complexity. Data analytics reshaped decision-making, from healthcare diagnostics to urban planning. Even creativity evolved. Music, art, and literature increasingly incorporated code as a collaborator rather than a tool. In essence, computation did not just automate tasks, it augmented thought. It expanded the boundaries of what humans could imagine and achieve. The very definition of intelligence broadened, encompassing both biological and artificial forms. By the early 21st century, computation was no longer a revolutionary force. It was the water in which society swam. Smartphones became extensions of memory. Cloud services externalized knowledge, and AI assistants mediated daily routines. The shift was so complete that many stopped noticing it altogether. The extraordinary had become ordinary, yet beneath this familiarity lay a profound truth. Computation had restructured civilization. It changed how we live, learn, work, and relate to one another. It created new possibilities and new perils, new freedoms and new dependencies. And it ensured that the story of human progress could never again be told without silicon, code, and the networks that bind them. The past 2 decades have seen computation undergo its most radical expansion, from powerful yet specialized machines to ubiquitous systems embedded in every aspect of life. What began as desktop tools has evolved into global infrastructures, personalized assistants, and even predictive intelligences. If the 20th century was the story of computers becoming mainstream, the 21st is the story of them becoming inseparable from the fabric of existence. In the early 2000s, computing pivoted from standalone machines to interconnected networks of devices. The rise of smartphones transformed pockets into portals. Apple's iPhone, released in 2007, did not just merge communication and computing. It created ecosystems of apps, services, and platforms that defined a new digital economy. Android quickly followed, ensuring billions of people around the world would live tethered to small, powerful computers. At the same time, cloud computing redefined scale. No longer confined by local hardware, individuals and organizations rented vast computational resources over the internet. Amazon Web Services, Microsoft Azure, and Google Cloud transformed computation into an on-demand utility, as foundational to modern economies as electricity. Perhaps the defining feature of the contemporary era is the ascent of artificial intelligence. Breakthroughs in machine learning, neural networks, and natural language processing have shifted computation from executing instructions to generating insight. AI no longer merely follows rules. It identifies patterns, adapts, and even creates, from recommendation systems that shape entertainment choices to large-scale models driving healthcare diagnostics. AI has become both pervasive and transformative. Tools like ChatGPT or Midjourney demonstrated that machines could generate human-like text and imagery, blurring lines between automation and creativity. These advances raised questions as profound as they were practical. What does it mean to think? To create, to decide? Parallel to AI's ascent, the frontier of quantum computing has begun to emerge. While still experimental, companies like IBM, Google, and startups such as Rigetti are racing to harness quantum mechanics for exponentially faster calculations. Unlike classical bits, qubits exist in superposition, allowing simultaneous processing of possibilities. Though practical applications are still limited, breakthroughs suggest a future where problems once thought intractable, molecular simulations, cryptography, optimization at planetary scale, may become solvable. In this sense, quantum computing represents the continuation of a journey begun with the abacus, redefining how humanity structures logic to confront the complexity of nature. The proliferation of sensors, smart devices, and connected infrastructure has created what some call the Internet of Everything. Cars, thermostats, factories, and even cities are now computationally aware, continuously gathering and exchanging data. Autonomous vehicles illustrate both promise and peril. The dream of safer, more efficient transport meets the challenge of ethical algorithms and security risks. Smart grids, precision agriculture, and connected healthcare similarly demonstrate computation's potential to optimize human systems, yet also raise concerns about surveillance, data ownership, and environmental costs. Today, computational power is both concentrated and distributed. The United States and China dominate AI research and cloud services, while Europe pushes for ethical frameworks and regulation. Emerging economies, meanwhile, harness affordable smartphones and digital finance to leapfrog traditional infrastructure. But this spread is uneven. Billions still lack reliable internet, creating digital divides that mirror and reinforce global inequality. The same systems that empower can also exclude, raising urgent questions about who benefits from computational progress. The contemporary era is also defined by reckoning. AI bias, privacy erosion, misinformation, and the environmental toll of data centers have sparked global debate. As computation grows more powerful, so too does its shadow. Energy-hungry mining for cryptocurrencies, algorithmic manipulation of politics, and the weaponization of cyber tools remind us that technological revolutions carry costs alongside benefits. Governments, researchers, and civil society are now locked in urgent discussions. How do we regulate AI? How do we balance innovation with privacy? How do we ensure computation serves humanity rather than undermines it? Perhaps the most striking feature of today's era is how computation has faded into invisibility. Algorithms curate news feeds, optimize traffic flows, and predict consumer behavior without being noticed. Digital assistants answer questions before they are asked, while predictive systems manage logistics with minimal human oversight. We live surrounded by computation, yet rarely see it. This invisibility marks both achievement and danger. When systems become so deeply embedded that they disappear, it becomes harder to question, regulate, or even recognize their influence. In sum, the contemporary era represents a convergence: AI, quantum experimentation, ubiquitous networks, and invisible algorithms, all shaping a civilization structured by code. The calculator, once a separate tool, has become civilization's nervous system, connecting, sensing, and predicting at scales beyond imagination. This is the moment we now inhabit, a world where progress is inseparable from computation, and where the next leaps will test not only technical ingenuity, but also human wisdom. Looking back, the journey from the abacus to quantum computing is more than just the story of machines. It is the story of how humanity reshaped its relationship with knowledge, time, and possibility. Each era of computation left a legacy that redefined what it meant to be human in a world increasingly mediated by numbers and logic. Before the abacus, calculation was slow, error-prone, and limited by memory. With its invention, merchants could track trade more reliably, and societies could expand economic networks. Centuries later, mechanical calculators liberated mathematicians from tedious arithmetic, enabling more ambitious exploration in science and engineering. The digital revolution, in turn, shifted computation from rarefied institutions into ordinary households, and finally into the pockets of billions. The cumulative effect is staggering. What once required years of manual effort now happens in seconds. Computation has not merely saved time, it has multiplied the scope of human ambition. Several aspects of modern life are unthinkable without this lineage. Global navigation satellites, precision medicine, financial markets, climate modeling, and even communication itself are all products of computational evolution. Every email, bank transfer, or streamed video is part of a living legacy stretching back to the first counters moving across wooden rods. Moreover, computation has altered the very structure of knowledge. Data is no longer just recorded, but continuously analyzed, modeled, and predicted. This shift has created new disciplines, computer science, information theory, artificial intelligence, that now sit at the core of every field from biology to linguistics. Each milestone inspired the next. The Abacus inspired mechanical devices. Mechanical devices inspired Charles Babbage's analytical engine. That unfinished vision influenced Alan Turing, who provided the theoretical blueprint for digital computers. The digital revolution gave rise to AI, and today, AI research inspires quantum approaches. This legacy is cumulative and recursive. Progress in computation does not erase the past, it builds upon it. Even in today's most advanced labs, researchers sometimes draw metaphors from the abacus to explain quantum phenomena. A reminder that the oldest tools still echo in the newest frontiers. Why does this matter in the grand sweep of history? Because computation marks a pivot in the story of human power. Just as the harnessing of fire, agriculture, and industrial machinery transformed civilization, so too has the harnessing of computation. It is the engine behind the modern world's complexity, from city planning to genetic sequencing. The legacy of this journey is not only technological, but civilizational. We live in a world where code, once abstract symbols, has become the infrastructure of reality. That is the true measure of computation's lasting impact. It is no longer just a tool of progress, it is progress itself. As we stand on the threshold of the quantum era, one question looms. How much further can the human capacity for calculation expand? For centuries, each leap in computing has seemed revolutionary, and yet every breakthrough has laid the groundwork for the next. Today, we are entering a phase where computation is not only faster, but fundamentally different in nature. Quantum computers, capable of harnessing the principles of superposition and entanglement, promise to solve problems that would overwhelm even the most powerful classical supercomputers. This could transform fields from drug discovery to cryptography, opening new frontiers of science and reshaping the global balance of power. But progress remains uneven. Quantum systems are still fragile, expensive, and experimental, leaving open questions about how quickly they will scale into practical use. At the same time, artificial intelligence is weaving itself into daily life in ways both subtle and profound. The integration of machine learning with advanced hardware is pushing us toward a future where computers do not merely follow instructions, but generate insights, simulate possibilities, and even make autonomous decisions. For some, this heralds an age of creativity amplified by machines. For others, it raises urgent ethical dilemmas about control, fairness, and dependence. Meanwhile, another frontier quietly advances: biocomputing. Researchers are experimenting with DNA-based systems that can process information at molecular scales, hinting at a future where biology and computation converge. Combined with quantum and AI, these hybrid approaches could redefine what we mean by a computer altogether. What will this future look like? Will quantum machines render current encryption obsolete overnight? Will AI become an indispensable partner in everything from art to geopolitics? Will computation itself become invisible, embedded seamlessly into our environments, our bodies, even our very thoughts. The trajectory is clear. Computing is no longer confined to machines sitting on desks or data centers. It's evolving into something ambient, adaptive, and omnipresent. Just as the abacus once expanded the human mind's reach, so too will these emerging technologies stretch the boundaries of what humanity dares to imagine. The future of computation is not just about speed, it is about possibility. And that means its greatest breakthroughs may still lie beyond the horizon. From the humble beads of the abacus to the shimmering promise of quantum processors, the history of computation is a story of humanity refusing to accept the limits of its own mind. Each generation built upon the last, merchants refining trade, scholars accelerating discovery, engineers unleashing machines that reshaped economies. And now, scientists probing the very fabric of reality with quantum logic. What once took lifetimes can now be achieved in seconds. More than just a technical evolution, this journey reflects the deeper truth that progress is not about tools alone, but about vision, the willingness to imagine, build, and trust in ideas bigger than ourselves. And yet, the story is far from over. The next chapter belongs to us, to use these machines wisely, to push discovery forward, and to ensure that technology serves humanity's highest purposes. If this exploration fascinated you, like the video, share it with others, comment your thoughts. Subscribe for more documentaries like this one.